Good evening, everyone. Thank you so much for coming. I'm going to do a really brief introduction because this night is not about me. I want to get straight to our amazing students. I just wanted to welcome you to the 6th annual McLean Science Lecture Competition. And this is, I can't believe it's actually been going for 6 years. I don't know how that happened, but the competition was named for a faculty member who didn't overlap with any of you, but he was a pretty legendary science teacher here at St. Andrews. His name was Dr. Peter McLean, and he was sort of infamous for his very passionate communication of all things science, especially science in the natural world. He loved to talk about the natural world and nature and encourage us to take better care of the earth, and we named this competition after him for his just love of talking about science with everyone and just really sharing his passion for it. And so with that spirit, we have 4 young scientists who have an area of passion of their own that they're excited to come and teach you about tonight. So you're going to hear 4 incredible talks, one after the other. You'll have hopefully some chance for Q&A, depending on how the timing goes. We're going to try and have time for Q&A after each talk, okay? So you will get a chance to ask a question if you have one. So be thinking of those during the talks. And then we also have a panel of judges of science faculty, and also Zach, who was one of the finalists last year, who's a student judge, who'll be listening to all the talks. And so there is an overall winner who won't be announced tonight because the judges need to sort of confer, and usually we run pretty close up to the time that you need to get back to dorm. So we'll actually announce the winner at school meeting next week. So tonight is just to listen and enjoy the 4 talks that we have for you. Okay, so I know everyone, all of our 4 finalists, Amanda and Daisy and Lindy and Ashley, are going to do amazing, and we're going to be so proud of them. And without further ado, I'm going to welcome Amanda to the stage.
All right, before I begin today, I just would like to speak on behalf of me and everyone presenting that we really appreciate you being here, and it really means a lot to us that we can share something we've worked on for a while with you guys. So, yeah. All right. When will I die? Using life events and machine learning to predict mortality and extroversion. In this age of advanced technology, our fascination with the unknown has led us to explore the mysteries of our own mortality and personality. Now, we find ourselves in a realm where computers are able to serve as perhaps fortune tellers, working to predict the unpredictable. And today, we'll be diving into the models, the data, and the predictions these computers are able to make. And through this, we're able to examine how machine learning propels us into a future where computers not only are able to comprehend, but also they can anticipate the nuanced shifts in our world. And before I begin today, I would like to ask the audience 2 questions. First one being, do you find AI scary? And if you do, please raise your hand. And keep your hands up. And out of the people who find AI scary, how many of you have a basic understanding of AI? Lacking. Well, the reason I wanted to give my talk today is because when I first posed this question to my friends, a lot of the response I got was, yes, super interesting topic. However, this is terrifying. I don't want to know when I'm going to die from a random robot. But I think a lot of our fear comes from our misunderstanding of this technology. And I hope my talk today serves as an interesting way for us to know and interact with the fundamentals of computer science and machine learning. And through this, we're able to better recognize and re-examine our relationship with technology and machine learning around us. And for the people who did not find machine learning intimidating in any single way, well, my intro was actually not written by myself, but rather the good old ChatGPT. That just comes to show how powerful machine learning models today has become, and this is a topic more relevant than ever. Now, we're going to have a little background or a crash course on machine learning. The topics we'll be talking about today is first, artificial intelligence, machine learning, deep learning, and natural language processing. Now, coming up with artificial intelligence. It's the idea where scientists coined in 1950 where humans are able to problem solve using our intelligence. And perhaps we can train computers to do the same tasks as us if we just imitated how our human brains work. Let's look at an example. Here we'll have a picture of a cat. We'll name him, let's say, Bob. And our human brains are able to recognize that this is Bob and Bob is a cat. However, could we train computers through imitating how we think and how our brains work to recognize that this is Bob and Bob is a cat? Right. Machine learning is now a subcategory of artificial intelligence. It's a machine's ability to learn without being specifically programmed. This is achieved through training through a large amount of data. The simple idea is just we throw data at it, we train it, and we teach it like a kid, and then it does what we tells it to do. There's different types of machine learning. Well, we'll be looking at an example of Stormy and Mr. Porter in this case, but supervised learning, reinforcement learning, and the one I'll be focusing on today is unsupervised learning. Unsupervised learning is taking a bunch of unlabeled data and giving it to the machine and telling the machine, hey, find patterns and categorize this data. For example, the machine will be given images of Mr. Porter and Stormy, and these images will be unlabeled, meaning they would not have this label on top of them. And the machine is able to recognize patterns within these data and find out which is a picture of Mr. Porter and which is a picture of Stormy. Now, deep learning is now a subcategory of machine learning. It's inspired by how our brains work, and thus we have to understand how the human brains work first, and then we can understand deep learning. So, neurons are things in our brains that fire and communicate with each other so that we're able to make decisions. And let's use an example with Mr. O'Connell. Mr. O'Connell sits down and plays a video game, Mario. But how does he know if this is Mario or Luigi? Well, he's given the information, his neurons fire, they communicate with each other, and they pick out the important information, such as his hat, his gloves, and his shirt, and makes an educated guess that, yeah, this is a picture of Mario right here. Oh, all right. With that, deep learning works much of the same way as how our brains work. Rather than neurons, we use artificial neurons, which are programmed into the computer. Since we already used Mario, let's talk about Luigi. Luigi is the input, or what our eyes see. The hidden layers decipher the information, or they interpret the image by breaking it down. And then we use an aspect called attention, which puts emphasis on things that are important, much like our attention. In this case, it's Luigi's hat and Luigi's shirt that tells the machine, yes, this is the important part of Luigi, and this is a picture of Luigi. Now, here's the easiest part. Natural language processing just means computers that are able to understand our language. They're widely utilized because it's so good with dealing complex in a large set of data. When you think about languages, French, Latin, English, all of these languages are so complex because they have so many words, grammar rules, and different words mean different things when placed in different time periods or different places. And now, natural language processing, because it's so widely utilized, it can be also built with deep learning and attention models. So, how does this work? We'll use another example. Now we have Dr. Walsh. Dr. Walsh once says there is the Riz and the Rizzler. In this case, the machine uses attention, or picking out the important aspects of a sentence, to interpret what the sentence means. And in this case, the word Riz and Rizzler would have a lot more weight in how they contribute to the meaning of the sentence compared to a word as there or and. Now, here's a summary of the little crash course we've done so far. AI is the broad topic that we'll be talking about. It talks about how machines is able to kind of imitate human behavior, human problem-solving behavior. Now, machine learning is a subcategory of AI, which is just we throw data at it, it does what we want. Deep learning is when AI or machine learning imitates how neurons fire and pick out the important information. Natural language processing is just machines are able to understand the human language. Now, Life2Vec, which is the machine learning model we'll be looking at today, is a cross-section between deep learning and natural language processing. So, what is Life2Vec? Well, Life2Vec is a machine learning model utilizing natural language processing and transformers. Now, what is a transformer? And sorry, we're not talking about this transformer, no Optimus Prime today. However, transformers are machine learning models that utilize attention, where they put emphasis on certain words based on where they're placed. In this case, we'll use an example. Mr. Tolton-Bitzer is chasing Sienna, or Sienna is chasing Mr. Tolton-Bitzer. The placement of the words Mr. Tolton-Bitzer and Sienna differs where they were placed, making two complete sentences with different meanings. Thus, transformers are able to recognize where a data is placed and how it contributes to its meaning. This will come back handy later on. So, how are we able to actually predict events, and how are we able to gather our data? Well, we utilize a similarity that all of us have, is that our lives are merely a sequence of events. We'll use Patrick as an example. Patrick is born, Patrick gets sick, we go to the hospital, Patrick goes to school or get a job, and Patrick might find his fun job and get married. A lot of our lives actually turn out to be quite similar. It's the same events, just occurring in different time frames and different periods. And thus, we're able to make our lives into a sequence of events of when it happened or what it happened. And going more on that. So encoding information just means how are we able to feed the machine the data. The data the data the scientists collected is from 6 million Danish citizens from a census, and out of these, 3.3 life sequences were created. Life sequences are simply sentences that represents what happened and when something happened in someone's life. And in this case is, in August of 2015, Dr. Hammond worked to find the cure to middle-aged balding. And sadly and unfortunately, evidently, Dr. Hammond did not. In a sentence, two aspects of information is encoded. Time, when this happened in 2015, an event. Dr. Hammond tried to find a cure for middle-aged balding. This information is encoded in the machine using a synthetic language, which just means fancy line of code so that the machine is able to understand it very succinctly. Now, what actual aspects do we actually look at when putting these informations together? The first part is when. It tells us the age and when and / the date where it happened. And the what, we'll be looking at two databases, the labor and health. In the labor database, it tells us when something happened, what industry you worked in, what city was this in, what was your income, and what was your position. In the health database, it talks about when something happened, your diagnosis, and its status, whether it be inpatient, outpatient, or emergency. All these information is stringed into a sequence of events, which represents what happened in your life and when did all this happen, which is pretty cool. And now, coming to the predictions. Here is a visual representation of all the prediction the machine is able to make, with the lighter yellow region resembling a low probability for mortality, meaning you'll likely survive. And over here in the darker region, you will have a high rate of mortality, meaning you're less likely to survive and more likely to die. And the red dots simply mean how many people actually died. We're able to see that, yeah, it does a pretty good job of estimating who's gonna die, since over here, there's only one red dot, while over here, there's, God, so many of them. And in the ones that have a high survival rate, we're able to see that this machine isn't perfect, since there's a couple specs here that still shows that some people died. However, when we look at these dots, we're able to see that the ones in the lower mortality rate section actually are the result of unpredictable circumstances, such as accidents and sudden onsets of illnesses that we couldn't predict. And now, how good is this model compared to others? Well, we found that it outperforms other state-of-the-art models by 11%. The scientists found that they outperform other models by 11%. And another interesting discovery is that the model is actually a lot more accurate with females of a younger age compared to males or anybody of the older generation. Now, influential factors. What factors contribute to the machine's prediction? In graph J over here, it encodes for survival, meaning The higher the graph comes out, or the closer the value is to 1, you're more likely to survive. Thus, if you're a person of high income or holds a managerial position, good luck. You're pretty likely to survive. However, image H here encodes for mortality, meaning if you're closer to 1, you're more likely to die. Thus, if you're a skilled worker or a machine operator, and I'm sorry guys, if you are a male, you're more likely to die. And you're actually a lot more likely to die since that value is very close to 1. And now, this machine is not only able to tell us when we are going to die, it's also able to tell us if we're extroverted or introverted. In this case, we applied this model, the scientists applied this model in order to predict how sociable you are or how much you like people. In this case, question 2 and question 3, we found that the Life2Vec model scored a lot higher on compared to the other model, which is the RN model, which is the most relevant state-of-the-art model that the scientific community has developed, which is really surprising since the Life2Vec model is not designed for predicting your extroversion at all. However, the RN model is. Thus, this just comes to show the diversity of the types of application that this model is able to achieve. Now, here is a visual representation of all the data the machine is able to be given. And similar to how we talked about unsupervised learning, how machines are able to find patterns within data. All of this data is scattered before giving it to the machine. However, we found that it did a really good job at categorizing the data, such as labor force, where you lived, your job, healthcare issues, income levels, which this is really interesting. Before we gave the machine the data, the machine had no idea what income level is. However, through interpreting and putting the data into a pattern, the machine is able to categorize income level from 1 to 100. But that's not to say this machine is perfect. In the health section, the machine actually errorlessly, with error, categorized cardiovascular implants with cardiovascular diseases, which is interesting and opens up more doors to explore about the errors of this machine and why has it encountered these errors. Now, can we actually predict when we die? Technically, no. Because each of our lives are so unique that we encounter so many individual circumstances. We don't really know what happens to us tomorrow or the day after. And as a result of our uniqueness, the machine is actually not able to produce an estimate on one certain individual. However, because of the good and vast amount of data the machine has been trained on, we're actually really good at predicting data and mortality on a bunch of people. Now, that's not to say without its limitations. Because the study is only done in Denmark, we're not really able to know what other things has impacted it, such as COVID and other countries. And also, because of the lack of regulations within this model, it's not really able to be used in real-world situations yet. But last and most important thing, hey Siri, when will I die?
I don't know the future. I didn't come here to tell you how this is going to end. I came here to tell you how it's going to begin.
Thank you.
I just want to know how you decided on this project specifically, like what drew you towards AI learning instead of some other field that you would be perhaps more intrigued in?
Yeah, actually, this was not the first topic I had in mind, and my first topic was actually done on nanomedicine, but this study kind of blew up on the internet, and there was just a lot of talk about like, how is this able to do this? And there's actually a lot of, I guess, web pages putting a scam saying like, I can actually predict how like you would die based off of this study. And that got me really interested. And I actually went in and read the study and I was like, wait, this is actually not that terrifying as it sounds. However, like, this is so interesting that I don't think a lot of people understand actually how AI and artificial intelligence works. So I thought it would be an interesting kind of segue into that. And because ChatGPT is something that's been on everyone's minds for like the past like year, and this is really similar to that. And actually, the reason why I used kind of references to ChatGPT and Siri is because they're actually based off like similar models. When you look at them, they're actually really similar. And so that's why. I hope that answered the question.
I was just curious, where would this, if it advances more, where would this kind of be applied in government, in policy, and for good, for bad, and how would they use it? Just curious.
Yeah, so the researchers, what they're focused on more is actually not how it is able to predict when we die, but what factors contributed to when we're gonna die and our socioeconomic status or health consequences. So when we look at these patterns, we're able to know that this caused early mortality, or this aspect causes health issues. And through policymaking, we're able to be more informed on people who might be disproportionately affected by those issues, and then we can make more informed decisions. Well, the data, yeah, that is what the data says. Yeah. So Mr. O'Connell's question is that, according to the data, one of the factors that is most likely going to contribute to your death is being a man. And what are some ways that we can work to reduce that or work to solve that? I'm not sure how to answer this question. I think a lot of those, I guess, more high-risk jobs, such as like people working in coal mines and other industries, they employ disproportionately a lot more men than women. And I'm wondering if that is a possibility within, if it contributed to men rather than women, since, hold on, let me pull back to this slide. Where was this? When we look at this, it's not only men, but however, also machine operators and skilled workers. And a lot of people in those industries are disproportionately men, so I'm wondering if that is a consequence of the machine thinking, hey, if you are a guy, you're more likely to die. So, and that's not to say, the machine still has flaws. A big problem in machine learning is the idea of bias, that because the data set you gave it was really skewed, or it was biased anyways, the machine will be biased towards, I guess, men in this case.
Okay. It can be unblanked. I just gotta. Okay, that works. Good evening, everyone. My name is Ashley McIntosh, And the topic of my lecture tonight is how transcutaneous electrical nerve stimulation can mitigate the use of opioids. Before we move on, I just want to give a slight trigger warning as the next slide depicts some of the harmful and graphic natures of drug use. So, this is home for me. Coming from the inner cities of New York, it is not uncommon to see pill bottles and needles and other remnants of addictive medicines lying on the sides of the road. It is also equally as common to see people with drug abuse disorders abusing these medicines in communities and public parks and other public spaces, on public transportation even. And so, a study shows that 82% of overdose deaths in 2017 were either caused by or involved in opioid, and there were more overdose deaths that year than of traffic fatalities, homicides, and suicides combined. There are many ways that one can come in contact with opioids, but the leading method of contact is through prescription. I doubt you need another study to prove why opioids are so problematic, but I'll give you one anyways. A shocking study reports that 60% of teens that end up trying or even becoming addicted to heroin started with prescription drugs. New York City government has shelled out over $8 million for my community in the Bronx alone to help combat this issue, which is just a small microcosm of the city as a whole, a small microcosm of the state, a small microcosm of the nation, and a very small microcosm of the entire globe. And so this is probably where you'd be expecting me to ask everyone to raise their right hand and to swear off drugs, but I'll leave that lecture for another time. Tonight, I want to tell you all about transcutaneous electrical nerve stimulation, which I will be referring to as TENS from this point forward because it's a bit of a mouthful to say, and how that can be used to mitigate and to control the use of opioids. So, what exactly is an opioid? We've heard these being called plenty of things. That's better. We've heard this being called plenty of things: opiates, painkillers, narcotics, and we've heard of a variety of them: hydrocodone, oxycodone, heroin, and fentanyl, which are of the illegal variety. And so, yeah, they essentially work the same way, where they bind to receptors in our brain, and they inhibit the transmission of pain signals. And so, as mentioned, the way that opioids work is they bind to receptors in our brain, and the three main receptors that they bind to are mu, kappa, and delta receptors. Mu receptors are responsible for the analgesic effects, and analgesic is a word for pain, so mu receptors are directly correlated with pain. Kappa and delta receptors are responsible for mood, emotion, and other physiological factors that are associated with pain. And the activation of these receptors inhibits the release of neurotransmitters involved in pain signaling, such as substance P and glutamate, leading to reduced pain perception. Opioids also activate the brain's reward center, which leads to feelings of euphoria and pleasure. It also includes the mesolimbic dopamine pathway. And opioids have very addictive properties, which lead to neuroadaptations that reinforce drug-seeking behavior. What exactly is TENS? Many TENS units look like this, where they have a battery-operated pack that have leads or wires coming off of them, and they are attached to electrode pads. And that's better. And they attach to electrode pads. And the way they work is it's the application of low voltage electrical currents to nerve pathways to the brain. So despite the rather fancy sounding name that comes with transcutaneous electrical nerve stimulation, electrical nerve stimulation is not foreign to many St. Andrews students. By a show of hands, how many of us have received STIM at AL? I am also part of that population, and I will. Pardon me. I am also part of that population, and I'll put 2 hands up because I am a bit of a klutz, as you can probably tell. Yeah, I should be put in a bubble. But yeah, electrical nerve stimulation works. We've used it before, and it works like that. If you've experienced it, yeah, that's exactly what that is. However, it is important to note that those units that AL uses, and if you've experienced similar, are used in more clinical settings, and it is not as portable or accessible as the one that I have depicted here. So, the main similarity between opioids and TENS is the fact that they're both effective in relieving pain. However, there are a slew of differences that range from the application to the side effects that come with both. As we know, opioids are very, very addictive, and they have a slew of side effects, a plethora of side effects, and that is one of the most common differences. TENS is associated with minimal side effects, the major of them being that there is a little bit of discomfort at the site of electrode placement, but that is very minimal, and that is one of the only. So TENS alleviates pain through 3 main mechanisms, the first of which being the gate control theory of pain, which says that there are gates in our spinal cords, and it was proposed by Melzack and Wall in 1965, and one of 2 things can occur. Either these gates can be open or these gates can be closed. And I'm pretty sure you're all thinking, well, duh, Ashley, that's how gates work. The special thing about these gates is that when they're open, it allows for the passage of pain signals through these gates, and when they're closed, it prohibits or inhibits the transmission of these pain signals. And so opioids have a very strong gate closing sensation, and which makes them effective in stopping pain. TENS does have the same sensation as well, which makes it just as effective. The other of these mechanisms is the stimulation of endorphins. And essentially, endorphins are the body's natural painkiller, and they are created in our pituitary gland and hypothalamus, which, and they bind to the same receptors that opioids do, which makes them effective in stopping pain as well. TENS helps to stimulate the creation of endorphins, which makes it an effective method of stopping pain. The third of which being the induction of neuroplasticity, and TENS helps to stimulate that in induction, which leads to alterations in neuronal activity and pain processing. And TENS has also been shown to modulate these neuroplastic changes by promoting neural plasticity and restoring balance to the pain processing pathways. So, what specific parts of the brain does TENS help to stimulate? The first of which being the somatosensory cortex, which is responsible for processing sensory information related to touch, temperature, and pain. And TENS application helps to stimulate this, leading to perception of tingling or buzzing sensations at the site of electrode placement. The second part of the brain that TENS helps to stimulate is the anterior cingulate cortex, also known as the ACC, which is responsible for emotional and cognitive aspects of pain perception. And TENS stimulates this area, leading to changes in pain effect and subjective pain experience. The third of which is the prefrontal cortex, which is responsible for cognitive control and modulation of pain perception in TENS, and TENS has been shown to modulate activity in the prefrontal cortex, leading to changes in attentional focus and pain modulation. The fourth and last but not least is the thalamus, which serves as a relay station for sensory information traveling from the spinal cord to the cortex, and TENS has been shown to influence the transmission of pain signals to higher brain centers. So the picture that I have depicted here shows the different orientation that one can use when they're creating their specific treatment. And on many TENS units, there are two channels or two or more channels where one can change the amount of voltage that goes through these channels that leads to a more specified and specialized treatment experience. And there are many studies that prove that TENS is very effective in treating pain, but I'll give you two tonight. The first being published in the JAMA Neurology, and it says that TENS significantly reduce pain intensity in patients with chronic musculoskeletal pain. And the second of which was published in the Journal of Pain Research, which concluded that TENS was effective in relieving neuropathic pain and improving quality of life in patients with diabetic neuropathy. And there are a plethora of other clinical research studies that prove this as well, the effectiveness of TENS. So, despite all of the studies that have gone forth about TENS, it is still subject to ongoing research, clinical implementation, and healthcare policy considerations. It has been shown to modulate pain in particularly musculoskeletal pain and neuropathic pain conditions. And TENS is generally very safe. I mentioned the one side effect that I'm familiar with, which is a little bit of discomfort at the site of electrode placement. But that's really minimal and really the only, and when compared to opioids, which have a wide variety of different side effects and harmful effects, TENS really does do a lot more, and it's generally very much more safe. TENS is also very accessible. You can buy a TENS unit on Amazon and select pharmacies, and they're very, very accessible, and they're pretty easy to use. So this is just the periphery of electrical nerve stimulation as a means of navigating pain. It has been shown to stimulate the nerves and the muscles of people who have completely lost sensation or are on their way to losing sensation in limbs or nerves. And I have studied percutaneous electrical nerve stimulation because I'm a little bit of a nerd, but that is the implantation of these devices onto one's spinal cord to provide pain relief for a very long period of time. And interestingly enough, over spring break, I met someone who was partially paralyzed and had this technology implanted on their spinal cord to relieve pain, and they had an external pack where they could turn it on, and it was used for pain relief. So I thought that was very interesting. That just about concludes my talk. Thank you all for listening and being an attentive audience, and at this point I'd like to take any questions.
Hi, thank you for the talk. I have a question. So, is there an extent of pain that TENS cannot kill, and how does that compare to opioids?
I'm sorry, can you repeat that again?
So, is there like an extent of pain that TENS cannot kill? Like, is it like if someone gets in a car crash and like is feeling so painful, like would TENS be able to like alleviate it? Like how does that compare to that of opioids?
So there's no harm in using opioids and TENS at the same time. So someone who has just come out of surgery might be recommended an opioid. However, to lessen the amount of opioids that they have to take in the case that they're experiencing a lot of pain, can also use TENS. I have to admit that I'm not sure about a certain level of pain if there is a cutoff, but they can do both. And yeah, I don't think that there is a limit to how much pain TENS can handle, if that answers your question.
Have there been any studies comparing the long-term relief attained from TENS treatment versus standard prescription drugs? And if so, what results did those studies show?
I want to say yes, there have been. That TENS is very effective in relieving pain over time, and it lessens the amount of opioids that one has to take. Yeah, opioids seem like much of a crutch in today's society, and the whole opioid epidemic was spearheaded because of the over-prescription of these medications. But using TENS to substantiate the use of opioids and provide pain, help with pain and to modulate pain perception can be helpful over a long period of time.
Hi, I just have a question about more of like your opinion on this topic. Do you think that TENS could be feasibly rolled out into places like inner city New York in order to combat addiction, and if it would be effective? Because like I would imagine somebody who's addicted to opioids, if someone like came up to them and was like, "We'd like you to pay for this treatment," they'd probably be opposed to it and would rather prefer to keep using opioids. And do you think the city of New York or like New York State as like a government would be open to it, considering the amount of money they've already spent to combat this?
I love that question. I think that TENS is a great preventative to addiction. I think there are many factors that play into one's addiction to opioids, and it's not just the feeling of pain. However, TENS is a really great way of dealing with this pain. I'm gonna share my opinion. I feel like this should be implemented on a global basis, and even just starting with the US. I think that it should be covered by insurance, and I think that it should be, for lack of a better word, hyped up by doctors in the medical field. I think that it should be the first base as opposed to prescribing medications, because it really is effective. In terms of the cost and who is receiving the money, because it is a non-pharmacological way of dealing with pain, I'm not sure. And yeah, I'm really not sure.
Do you think that too much of TENS can be like a cause of more pain? Or do you think that like no matter how much TENS you use, that's like a good thing? Do you think too much of it is like a problem?
In my own experience and in my own research, I don't think one can become addicted to it. And even if they do, it can't harm them in any way. So if they like it, I like it for them. If they like to use that way of curing their pain, I don't think it can pose much of a problem more than uncomfort at the site of electrodes. If it is used properly, and I mentioned that it's pretty easy to use, but there is also the possibility of misusing this form of medicine, for lack of a better word. Yeah, but I don't think one can become addicted to it. Yeah, and it shouldn't cause any more pain by using it. Thank you. You got this.
Hi everyone. Today I'll be talking about the Einstein ring and the gravitational lensing of distant celestial objects. So here what we are seeing is an artist's illustration of an Einstein ring. In the center of this image, we see a light source that is emitting light, and we see something like a ring, and maybe that's where the Einstein ring got its name from. But this ring seems to be like a bubble or a magnifying glass that is in front of the light source. This ring seems to be magnifying the brightness and the size of the light source. And this magnification effect is actually what we call gravitational lensing. It's one result from the gravitational lensing, in fact. And the Einstein rings are classical examples of gravitational lensing. So before we can understand what an Einstein ring is, we need to talk about gravitational lensing. So in simple terms, gravitational lensing refers to the distortion of light by gravity. If we put these two images side by side, we now know that the light source in the image on the right is coming from a distant object, whether it is a galaxy or a star. And the light, because of the effect of gravity, is traveling around the middle object. And from our perspective as the observers, we are seeing a lensed image. For example, in the case of the Einstein ring that we are seeing on the right. And before we talk about more in depth about the physics behind gravitational lensing, we need to introduce our central character, the famous Albert Einstein. So according to Einstein's theory of general relativity, gravity is the distortion of space-time. Essentially what this means is that the greater the mass an object has, the more it is able to use gravity to distort the space fabric around it. It is able to push and pull the space fabric around it. And so, as you can see in the image on the left, the space around an object becomes curved. And when light is traveling through a curved space, it is actually traveling through these curves because that is the shortest path between the two points. This is the concept, what is called geodesics. And now if we go back to this image, we understand why the space around the massive object in the middle is being distorted in such a weird way. And the distant object, the light coming from this distant object is going around the massive object instead of traveling in a straight line. And just to reiterate something really important, during my talk, please keep in mind that the distant object I'll be referring to as the source, or the light source. The massive object in the middle is the lens, and we are the observers. Back to the Einstein ring. Einstein rings are classical examples of strong lensing, which is one of 3 types of gravitational lensing. The other two types are weak lensing and gravitational microlensing, which I'll talk about briefly at the end of my talk as an extension. I'll be mainly focused on the Einstein ring and strong lensing. So, the Einstein ring appears when light from a galaxy or a star passes by a massive object en route to the Earth. This image is very similar to the one that we just saw. The only difference is that the observer, the lens, and the source are in a perfect straight line. This is a necessary condition for us to observe the Einstein ring. It is even shown clear in this animated image over here. We see that when our perspective, the white light and the blue light are in a straight line, like over here, we see a perfect ring. And secondly, what we need is the mass distribution of the massive lens to be approximately axially symmetric. What this means is that the distribution of mass has to be somewhat even surrounding an axis. This is important because we know that mass is correlated with gravity. And if a mass distribution is uneven, then the gravitational effect that this mass has wouldn't be even surrounding it. So when light is traveling through the curved space, the curve wouldn't be symmetric, and we wouldn't be able to observe a ring. So that's essentially how it works. Here are some images of Einstein rings taken by the Hubble Space Telescope. As you can see, some of the rings are more complete than others. As we talked about, this might be a result from alignment or the mass distribution of the lens. Moreover, you can see that the light source in these images appear to be brighter and bigger than usual. This is also an effect from gravitational lensing. Gravitational lensing not only distorts light, meaning that it creates this ring, it also magnifies light. So, as we talked about, the Einstein ring is predicted as part of gravitational lensing, as part of the theory of general relativity. This happened in 1912, 4 years before Einstein's publication of his theory of general relativity. 12 years later, Russian scientist Orest Kovasin first mentioned in an article that a perfect alignment between the source, the lens, and the observer would produce a halo effect. Another 12 years later, Einstein predicted that the ring would be almost impossible to observe. In fact, in one article, he wrote that, quote, "Of course, there's no hope of observing this phenomenon directly." This, as we know now, Einstein is wrong because we've already seen pictures of the Einstein ring. What Einstein originally thought was that the Einstein ring has to be lensed by a star, which means that the middle object is a star. But if we consider other possibilities, such as galaxies or black holes, these celestial objects that have a greater mass, the likelihood of observing an Einstein ring would be a lot greater. This is all because of this equation over here. So, let me explain. On the left, data is a variable for angle. And in astronomy, angle can be used as a measurement of distance. If we think of our sky as a dome, or in 2 dimensions, a circle, each object in the sky would occupy a certain degree in the night sky. The moon, for example, its diameter would be half a degree arc angle in our sky. So using arc angle, we can, in the case of this equation, data refers to the radius of the Einstein ring. And if we ignore everything else on the right but big M, we know that higher the mass of the lens, the greater the radius of the Einstein ring. So the bigger the radius, the easier it would be for us to observe them. Einstein originally thought that the lens has to be the star, which has a pretty low mass compared to galaxies or black holes. So if we consider these objects with higher masses, it makes sense that it would be easier for us to see the Einstein rings. So, in 1987, a group of researchers observed the first Einstein ring. But at first, they couldn't figure out what it was because Einstein already told the world that the Einstein rings are impossible to be seen. So this group of researchers tried to come up with explanations to make sense of what they were seeing, but only the explanation of an Einstein ring was consistent with all the observations that they were getting. So they published their finding in 1988 of the first observed Einstein ring. A decade later, in 1998, the Hubble telescope observed the first complete Einstein ring. One of the scientists in this group of researchers disclosed that, quote, "At first sight, it looks artificial, and we thought it was some sort of deflect in the image, but then we realized we were actually looking at a perfect Einstein ring." As I briefly mentioned before, the Einstein rings are examples of strong lensing. The other two types are weak lensing and gravitational microlensing. These distinctions are made between the lens and the alignment produced by different, it's producing different lensing effects. So, as a review, strong lensing, such as Einstein rings, have massive lens. This is what we talked about in the equation. And it would also need a very accurate alignment for us to see a perfect Einstein ring. So as you can see in this image, which is a real image taken of an Einstein ring, it has a certain degree of magnification of the light source and distortion of light, which refers to the ring, almost complete Einstein ring, as we see in this case. Weak lensing, on the other hand, has less evenly distributed lens and less accurate alignment. You can think about weak lensing as if it's on the same spectrum as strong lensing, but on the very other end. So we can still see some degree of magnification in these, whether it's stars or galaxies, but there's less distortion. We see some arcs that's being created by the effect of gravity, but it's not enough for us to recognize a complete or almost complete ring. Gravitational microlensing, on the other hand, is very different. It has less massive lenses, such as planets, but it also needs very accurate alignments. As you can see in this image, animated image over here, we see that a planet and its host star are passing in front of another light source. So when they're passing through it, the brightness of the light source behind it is being magnified, but this brightness doesn't dim until the planet has all the way passed through the light source. If we plot the brightness against time, we see that the bigger curve is caused by the host star. But we see that a small peak follows, and that is the result from the planet. So gravitational microlensing can actually be used as a very good way to detect distant exoplanets. This is actually a very new field in astrophysical research. And since the first detection of exoplanet using this method, which was made in 2003, there has been more than 200 exoplanets discovered using this method. I won't go into details in my talk, but if you're interested in learning more about gravitational lensing, you should take Dr. Hai's astronomy class, because we discussed this method a lot deeper in that class. So, back to gravitational lensing. Whether it is strong lensing, weak lensing, or microlensing, they can help us understand distant celestial objects like exoplanets, stars, black holes, and galaxies. Because of their magnification effect, they can act like a second telescope. They can help us detect things that we cannot otherwise detect using the technology we have right now. They can also help us better understand the light source. The Big Bang theory, which suggested that everything in the universe once started at one singular point and has been expanding outward ever since, can also be confirmed and further understood using this method. Because gravitational lensing deals with these distant celestial objects, as the Big Bang theory suggested, as the further away these objects are, the earlier they're supposed to be of the universe. So gravitational lensing can help us better understand the early universe better. Moreover, the accelerating expansion of the universe, which basically just means that the expansion rate of the universe is getting faster and faster, The theory of the accelerating expansion often have to do with dark matter and dark energy, which is a very active in research field in astrophysics. And gravitational lensing can help us to gain better insights into these fields as well. So I've collected a few research papers done in the past 2 months. They are published in the Astrophysical Journal. A lot of them used gravitational lensing to learn more about black holes. In fact, a group of researchers used gravitational strong lensing to detect this ultramassive black hole that can fit more than 30 billion solar masses. So it's ultramassive. Researchers have also used gravitational lensing to learn more about dark matter, the structure and distribution of dark matter. In fact, one article has claimed gravitational lensing to be the most successful way yet to learn about dark matter. I won't be able to go over the finding of dark matter and black hole in detail in my talk, but I'm certainly willing to answer any question that anyone might have about these research. And thank you for listening.
So I assume the kind of radiation you talked about was all visible light. Do you think that the other forms of radiation, such as like gamma rays, X-rays, radio, or infrared, are these also warped by the bend of like space-time? So like, are there like their own versions of the Einstein rings attached to these different forms of radiation?
I believe so. I think what we talked about mainly is visible light, but I think in the detection of the first Einstein ring in 1978 and 1988, in these two images, I think these are all light in other wavelengths. I think this one, for example, is an infrared wave light, and they recolored it so that we can see it better. The short answer is yes. I think all different wavelengths should obey the law. Basically, it like travels through the curves created by gravity.
Hi. Why did you choose this topic?
I think partly the reason why I chose this topic is because I was in Dr. Hai's astronomy class, and we talked a lot about, in our unit about exoplanets, we talked about gravitational microlensing, which I briefly mentioned in this slide. And I found that very interesting, so I've always wanted to learn more about it. And so that's why I chose astronomy as my topic. And then I did a little bit more research, and the Einstein ring really interested me, and that's why I chose this topic.
Oh, and follow up. Do you plan on pursuing this sort of field, like in a career or something like that?
Maybe.
You touched on dark matter earlier. Have we found evidence of, dark matter with mass impacting light through gravitational lensing?
Here's what I'll say. All the evidence we have of dark matter right now are indirect evidence, like we have of black holes. We can't directly detect them, but we can observe them through their gravitational influence on the objects around them. So in terms of dark matter in this case, using gravitational lensing, researchers have been able to determine the structure and distribution of dark matter, mainly through learning about their mass. Going back to this equation, we know that this is referring to the mass of the lens, but it's actually referring to both the visible mass and the dark matter. So if we actually know what the visible mass is, we can eliminate that out and use our observation of the Einstein ring to learn more about the distribution of dark matter. Does that make sense?
Thank you.
Daisy, thank you so much for your talk. This is absolutely fascinating. So what you talk about how like if you go to like, I think the second slide, like the middle object, like that light gets magnified when, through gravitational lensing. When that's a black hole, how does that work? Because my understanding of black hole is that there's no light that would be magnified.
Right. Okay, so I actually did a little bit of research on this. For when the massive object in the middle is a black hole, it actually works the same way. Because black holes have such a great mass, its gravitational influence on the space around it, like it curves it, like we talked about. So like in this image, it's able to like dent the space. And so when light is traveling through it, it's actually not able to be absorbed by the black hole. It's gonna go around it, like it would in the case of a galaxy or a star. So it wouldn't go into the black hole, would be eaten by the black hole, but it would go around it. So it would work the same way as any other lenses.
How does the effect of like other objects within the lens like change the perception of the image?
Sorry, can you repeat that?
How does like other objects within, like if they're nearly the massive object, how does that affect the perception of the image, like the thing on the behind the massive object?
So you're asking like if there are any other objects in the middle between the light source and the observer?
Yeah.
Actually, before this talk started, I was doing some last minute, like just checking. Actually, if, for example, there are 4 objects aligned, us the observer, and then there are like 3 more things that we are seeing in a straight line, it might be able to create a double ring for the Einstein ring. So actually, you would actually see 2 rings. There is one example that the researchers have found, I think, a few years back, that there are 3 galaxies aligned, and for the image that we took, we're able to see 2 Einstein rings. So it's pretty cool.
Okay, yeah, I'm good. Did I do it right? Oh yeah, I'm ready, sorry. Okay, so just to start a little bit, just to give you guys a little bit of background before I start talking about this. If you don't know, I live on a tree farm. My dad bought the farm in 2003, so it's kind of like a 4th child in our family between my older sister and I. So my entire life, it's kind of been a topic of plants and trees and kind of the innovation and experimentation that's happening in that field. So for my entire life, this has been something of interest that my dad's been talking about, and it kind of happens at our dinner tables every night. So that's kind of why I wanted to talk about Mother Nature's secret solution to climate change. But first of all, if you don't know, I'm a huge Taylor Swift fan, but you also have to consider her flaws. And she was the American celebrity with the highest carbon emission in 2022, which is roughly 9,000 tons of carbon, which is a ridiculous amount compared to that of the average American and especially that of the average European. But I want you guys to remember this number for later because Taylor Swift specifically, her carbon emission comes from her private jet use. And her private jet use came from obviously her world tour, but also, remarkably, she took a 9-minute flight to go to the grocery store in 2022. And this 9-minute flight was tons of carbon emission that could have been avoided. But this carbon emission that we're talking about specifically here comes from transportation, which means all of that jet fuel, that gasoline, the diesel, the coal that you're burning to power transportation, all of that emits carbon. And this carbon emission leads into the greenhouse effect. So the #1 leading greenhouse gas for our purpose right now is carbon. And carbon, yes, it's all through the atmosphere, but this excess of carbon that's created from the excess carbon emission through these previous burning of different states of carbon, that's what our issue is. So these greenhouse gases have this quote-unquote greenhouse effect on the planet, which means that as heat from the sun is coming into the atmosphere, this blanket of chemicals that is covering our atmosphere, it's trapping the heat in there and it's leading to a rise in global temperatures. So these effects, which I'm sure that you all know about and that you've all heard about and seen, more recently, it can lead to the melting of the ice caps, which is displacing the animals in those regions. Wildfires are becoming intensified and longer and more frequent, and then tropical storms and coastal storms have a higher intensity and they have a higher occurrence too. So, back to talking about carbon. I'm sure you've all learned about the carbon cycle in freshman bio. Even if you don't remember you learned about it, you did. So, the carbon cycle, there's no doubt that like all life on Earth is carbon-based. It's everywhere. It's what we breathe out, it's what plants breathe in, it's what we're made up of. So all of this carbon, it exists, but the problem comes when we have an excess of carbon in the air in its gaseous state. So when we have this carbon in the air in its gaseous form, plants take it in the form of CO2 and takes it in through the stomata of the plant, and then it undergoes photosynthesis, which breaks it into its carbon and its oxygen. And so the oxygen then gets released out of the plant, that's what we breathe in, and the carbon goes and becomes the stuff of the plant. It's the building blocks of the plant. So it's the sugars, the amino acids, the proteins, and most importantly, it's the cellulose, which is the cell wall of the plant. So every single plant cell has a ring of carbon around it, which is incredible when you think about how much carbon is involved in not only like a small like plant on the ground, but let alone in us as well. So once it's in that solid form in the stuff of the plant, it goes, it leaches out into that soil over hundreds of years. It's a super long process, which is what makes it great, because that carbon, when it's not in the air, when it's in solid form in the ground, it's harmless to us, and that's part of the cycle, which is great. So over hundreds of years, it's leaching back out into the soil, and then it will eventually become gaseous carbon again, and the cycle is complete. But now for a history spiel, the problem began in the latest phase of the Industrial Revolution, which happened around the turn of the century, so the early 1900s. More specifically with the combustion engine, but that's a different thing. So at the beginning of the Industrial Revolution, you had this you were trying to account for this new mass transportation, mass production, factories across America, and in later dates, the internet, and powering the internet. And because of this increase in all these different types of things that you had to power, you had to pull from new energy sources, which unfortunately led to burning fossil fuels, which means taking up that carbon from the ground and using different forms of it. And the worst is burning carbon itself, burning coal to power things. So when you have this, you're putting out and you're expediting that natural carbon cycle at such an exponential rate that you upset the balance between gaseous carbon and solid carbon, which is when that greenhouse effect starts taking place. So the good news is that there is a solution. And you might be wondering, well, if there's a solution, why haven't we seen it already? We should know what it is. But that's because it's all around you. Because every single time you drive into campus, you pass it. And every time you're on the highway and you look out and you see an empty field, that's your solution to climate change. And that is how you cool down this planet, because it's called cover crops. And not only are they really cool, and not only do they cool down the planet and reverse climate change, they also look really pretty sometimes. So you have all of these different types of plants, and these cover crops are planted in the off-season of cash crops. So cash crops are what you think of that farmers plant and harvest for profit, like corn and beans and wheat and barley and things like that that they sell. And that's how they make their money. But cash crops are only in the ground for about half the year. So you have an entire 6 months of the year where you have bare dirt and bare soil, and that has no benefits at all. When you have bare dirt and bare soil, all you're asking for is wind erosion and water erosion and nutrients leaking out of the soil that you could be using somewhere else. So cover crops kind of prevent this shift and this negative impact of the soil. So what makes cover crops super cool is how deep their root system goes. So for reference, I'm 5'3", and the deepest of these roots goes 5 feet into the ground. Which might not sound like a lot because I'm not that tall, but it is really deep when you're comparing it to the top 2 to 4 inches where most root systems go in the top soil. So, talking about different types of soil, what's super important about the soil and the root system of plants is that soil organic matter, which is the plants and animal parts that are decomposing in the soil at any point of their decomposition. And all these things, if they were alive at one point, even if they're dead now, they're holding that solid carbon, which is what we want to see. So a good and healthy soil has about 3 to 6% of soil organic matter. Which you might not, it's a pretty small number, but when you increase it by 1%, that's a big increase. So just in case you were wondering what this actually means and you wanted some numbers, $30,000 cars over 20 years, which is roughly 1 million metric tons of carbon. And I'm struggling to articulate how much carbon that is that you are offsetting by simply putting into use about like half of the East Coast and all of that farmland there. You are offsetting a ton of carbon. And to put it into reference for all the St. Andrews students, at St. Andrews, a 1% increase in the organic matter of your soil on our 2,200 acres offsets about 900 cars, which is roughly 4,000 metric tons of carbon, which again, it's a ton of carbon. And if you keep this process going annually and you're using it and you're maximizing its ability to do what it's meant to do, you're able to keep that in the soil for a super long time, and therefore you're able to offset so much carbon just year round, having it do it by itself without your intervention. But going back to Taylor Swift, less than 5,000 acres of land, so about twice the size of St. Andrews, will offset her entire carbon emission. As the leading celebrity who had the most amount of carbon emission, you can offset all of that in only a few years, which is incredible when you're considering how much that we as a school would produce or that the average person would produce. This is crazy, and it's doable. It's the best part is that it's something that we can act today, that St. Andrews could have a part in solving and fixing and working towards. So again, 44% of the United States is zoned agricultural land, which means 44% of the United States could be put into use to solve climate change. And this is talking about the United States only, not even accounting for the rest of the world. So it's 878.6 million acres of land that you could be using the entire year to be offsetting carbon emission and to be stopping this imbalance between solid carbon and gaseous carbon. And here is how we do it. It starts with the education of farmers, and there's a super cool thing at all state universities called, I think it's called the Ag Developmental Program, which basically helps educate farmers on modern farming techniques, which are things like cover crops that are really helping you to reap the benefits of new and modern and innovative farming, which is super cool because, as I said before, this is the way that you make change. You start small and you understand that it might not be effective for everyone, but the way that this begins and the way that you begin to offset this carbon emission, the way you begin to solve all of these environmental problems is you begin with something small, like educating the farmers that are responsible for this change, that could bring this change to America. So to summarize, the solution to climate change is all around us, and every single one of you could have a part in reversing it. So this is kind of my call to action for you guys to all, if you weren't paying attention before, pay attention now, because all you have to do is look up the word cover crops, and all of a sudden you will have products popping up for you to buy and for you to plant in your backyard that you could take a part in this reversal of warming up the planet. And even as you can see here, they look so cool. Like, why wouldn't you want to do that? And they're so beneficial too. I just can't say enough good things about them. So I was wondering if you guys had anything to say about it. So if anyone has any questions, please let me know.
How does tilling the topsoil affect the plants? Like how and why?
Oh, that's a good question. So I can, oh, this might take, oh, wait, hold on. Wait, no. Okay, so when you're tilling the topsoil, this is only looking at cover crops up here, so that's where you see all the deep root systems, but when you have other crops that are in the soil for not as long or that have a naturally shorter root system, when you till those top 2 to 4 inches of soil, that's when you're kind of, that's also another way that you kind of speed up the process of the carbon cycle, because you're adding unwanted oxygen, unwanted air to this soil and this root system, which is speeding up that process of breaking down that carbon, which isn't what we want, because we want that carbon in that solid form. So the best way I can explain it, it's like when you're speeding up the process, it's kind of like if you have like a kindling fire, it's like blowing on it and it's just getting it like super big that you don't want. Like you want to like put it out and keep it in that ground for a really long time.
Hi, are there any plans for the U.S. federal government or any governments around the world to enact any subsidies for cover crops in the future? And if not, do you foresee that happening anytime soon?
I couldn't really hear you, but are you asking about if there's like government policies enacted for these?
I was just asking, is the U.S. federal government planning on subsidizing the planting of cover crops, or are they doing this already?
I really think that as of now, given that it is like all of this education about it and the starting of it obviously stems from the education of the people that are doing it and the education of the farmers. And as of now, there are no government policies or plans to subsidize this, this technology in this method of farming. So I can't really say that I see this happening in the future, because I think at this point, usually the governments around the world are kind of focusing their attention on the advancement of other technologies that most of the time are contributing to this problem of climate change. So I don't really know if this would be a huge focus in the future, but it definitely could be, and that's definitely something that I could look into, and I wouldn't be surprised if this becomes a topic of discussion over the next few years.
Are there any foreseeable downsides to using cover crops, or why hasn't it been like widely adapted in most farms?
Really, why it hasn't been used as much now is like basically because modern farming techniques, sometimes it's hard to communicate the benefits to the people that would be using them because they're so used to their old methods. It's also important to consider that it would be hard to start turning over a field completely new that you are used to leaving bare. Even though it would have so many benefits, sometimes it's hard to convince people that your long-term benefits, that your nutrient density in your soil would be increased, you'll have less erosion in your soil, and you'll have more organic matter, which is healthier soil. You really have to look at the long-term effects of these things, not only climate change, but also for the farmers themselves, who are supposed to be considering the health of their soil and therefore the health of their plants. It's difficult for them to understand that this change to their methods that they've been used to is really beneficial in the long run, even though the short term might be difficult and even probably costly to change their method of not tilling the soil and buying new seed packs and spending the money for the manual labor to get that done.
Hello. So I was wondering, so like the Earth, like I was wondering, like has a natural like balancing act, you know, like when like a species dies, a lot of times it can come back up because like the species that hunts that species can't like eat the other species. So I'm wondering, like, cause climate change would warm the Earth, if the Earth is warmer, wouldn't like the ice melt in the like polar caps and where there's ice, and then wouldn't plants grow there because it melted, and then wouldn't those plants eat the carbon in the Earth? So then wouldn't it like balance back out because there's more plants that are being like grown?
It's a very complex question. I appreciate it. My best, I'll say this, is that I haven't studied evolution and kind of the endangerment of species that carefully, so I can't really speak on that much, but I do think that you have good thinking on like what it would mean to be like, to see carbon and see this plant life growing in different places, but I don't really think I can answer your question. I can't do your question justice right now with the amount of knowledge that I have, so I'm sorry.
Okay, that brings us to the end of the evening. The judges will now confer. One more big round of applause, if you would, for our speakers. Woo! Thank you, everyone. Have a great night.